Hi, Doctor. Our topic is critical evaluation of the kinematic design of a hand skeleton with flexion and abduction motions. Our work presents a critical evaluation of a hand skeleton mechanisms described by FABA. The main focus is to review its kinematic formulation, determining the extent to which it can be reproduced using published information, and supplement the study with a preliminary dynamic evaluation to analyze aspects not addressed in the original article. FABA mechanisms consist of three closed loop RRRR, RPSPU, and URSU, with 2 degrees of freedom, theta2 for flexion and extension, and D25 for abduction and adduction. Our work doesn't not modify the mechanisms, we only reconstruct the original model, evaluate the reproducibility, and add a preliminary dynamic analysis. The problem is not that FABA mechanism is incorrect, but that work mainly focus on kinematic analysis, and some information required for independent reconstruction is unavailable. Therefore, our object is to evaluate the reproducibility of the model and explore the additional insight provided by a preliminary dynamic analysis. The mechanism is reconstructed has a 3 interconnected closed loops, RRRR, RPSUP, and URSU. The 2 independent input, like theta2 and D25, this input propagates sequentially through the loops, which loop determines the variables required by the next one. The final output, theta 9 and alpha 9, describe the final orientation of the mechanism and used to evaluate the motion quality.
Okay. Equation and numerical reconstruction. After defining the kinematic model, we solve the geometric constraining of loop 2, the RPSPU loop, using theta2, D25 as input. The unknown variables, theta7, phi7, and D67 were obtained by solving the nonlinear closure equation numerically in Python, and the closure residual was then evaluated to verify the consistency of the solution. Therefore, when the 55 changes from 25 to 4 millimeters, the corresponding values of phi7 from 10 to 20 degrees are the solution provided by the solver. The results show the internal kinematic response of loop 2 while maintaining geometric closure. It is not the final coupling evaluation, which requires the loop 3 outputs. So as an extension of the kinematic analysis, we perform a preliminary dynamic evaluation using a simplified one-doof finger model. The objective is to compare the torque considering only gravity versus a model that also includes acceleration effects. Okay, preliminary dynamics. After reconstructing kinematic models, we perform a preliminary dynamic evaluation using a simplified one-doof finger model to estimate torque requirements during inflation. A circular trajectory from 0 to 90 degrees in 1 second, with defining the angular acceleration we obtain from the secondary by the dynamic torque. We calculate S, this equation. The first term represents the inertial torque, while the second represents the gravitational torque. The equivalent inertia was obtained from the simplified finger model considering the phalanx contribution. So using the dynamic formulation, we calculate the torque required during flexion by comparing a quasi-static model based only on gravity with a dynamic model that includes inertia. The difference between both models correspond to the inertial contribution, which increased torque during acceleration and assists the motion during deceleration. The maximum torque obtained was 7.63 millinewton-meters. This value corresponds only the simplified one-doof finger model and not to the complete 3-loop mechanism. So the conclusion, the initial approach was correct by the reconstructing the actual FABA mechanisms. Loop 2 and 1, 2 were resolved and numerical with negligible closure errors. The preliminary dynamic analysis showed the torque requirement change during acceleration, and this acceleration can be determined from position analysis on. And the next step is complete the geometric of loop 3 and extend the dynamic analysis to the entire mechanism. Thank you.